We have seen that for the constant force F and the displacement d, the work is 4 times the distance. Assuming that we are moving an object from point A to point B, and the force is not constant, perhaps it is more difficult to move the object during the first part of the journey than the rest. Then the work is no longer the product of the 4 times the distance. The force is a function of x, the position of the object on the interval a, b. The force used to move the object a distance delta x, which is small, can be assumed to be constant. Then the work needed to move the object a distance delta x is f of xi times delta x. We will call this wi. This is the work needed to move the object a distance delta x at x equals xi. The total work needed to move the object from x equals a to x equals b is w equals the sum of all of these wi. Each wi is the work needed at xi. I go from 1 to n. This is the sum as I go from 1 to n of f of xi times delta x. But at n go to infinity, we recognize that this is the Riemann sum, f of xi times delta x. This is the definite integral of f of x dx at x go from a to b. This result is also true even if the force is not constant. For example, how much work is done raising a 4-pound weight to a height of 16 feet above the ground? We can find the work by taking the constant force times the distance, 4 times 16, 64 foot-pound. Or we can find the work by integrating the constant force along the x-axis from x equals 0 to x equals 16, and we still get 64 foot-pound. An example, a 45-meter rope with a mass of 30 kilograms is dangling over the edge of the cliff. Ignore friction. How much work is needed to pull the rope up to the top of the cliff? A very wrong approach is to assume that the force is constant. It is absolutely wrong to find the work by taking the 4 times the distance. The force is the mass times the acceleration. This is not correct because the force is not constant. The force that is used to pull the entire rope at the beginning is not the same as the force used to pull the remaining part of the rope halfway. In this case, the force is not constant. We will need to use calculus somehow when the quantity is not constant. We position the rope on the coordinate axis so that x equals 0 is at the top of the cliff, x equals 45 is at the bottom of the cliff. If we can pull the entire rope up at once, delta x at the time, then we can assume that the force is constant. The remaining part of the rope needed to pull up at any time has the length of xi. The work at that point is the force times delta x because we move the rope delta x at the time. It is ma delta x. If the entire rope, 45 meters, has a mass of 30 kilograms, then the length x meters has the mass of 2 over 3x kilogram. So the mass is 2 over 3xi, acceleration is 9.8, the distance is delta x. The total work is the sum of all of these wi. This total work is the Riemann sum, so as n goes to infinity, we end up with a definite integral. We add up all of the delta x from x equals to 0 to x equals 45. The total work is 6,615 joules. Alternatively, this might be better. We slice the rope into many length segments of delta x, and we pull this length segment delta x a distance of xi, so we can assume that the force is constant because it is a tiny segment of the rope. The force is the mass times the acceleration, and the distance is xi. The mass of the delta x part of the rope is 30 over 45 times delta x kilogram. And so the work to move the delta x length segment of the rope to the distance of xi is 2/3 delta x times 9.8 times xi. The total work is therefore the Riemann sum. As n goes to infinity, this Riemann sum will give us the definite integral, and we add up the slices from x equal to 0 to x equal to 45. The work is still 6615 joules. We did this problem using two different methods. One method, we pull one tiny segment of delta x up at the time, so we can assume that the force is constant. Previously, we pulled the remaining part of the rope up a distance of delta x at the time, so the distance is constant. Regardless of which methods we choose, we need one of the quantity to be constant so that we can use W equals F times D. Work is the product of 4 times the distance if the quantity is constant. Note also that if we were to position x equals 0 at the bottom of the cliff and x equals 45 at the top of the cliff, then we would move the delta x segment of the rope up a distance of 45 minus x instead of xi.